Hello, and welcome to the sequel in our Introduction to AI series of lectures as part of MITRE's Generation AI Nexus program. Let's briefly recap where we came from. In the prior lecture, we introduced the broader field of artificial intelligence and the framework of computational rationality, which was all about creating artificial agents that are able to maximize utility functions or minimize some type of loss function. We also discussed that artificial intelligence is really broken up into four different subfields. And of course, the lines between these, though I have drawn them in solid, bold color, they really are blurry, especially nowadays with the confluence of various technologies. Let's review the main topics that each of these subfields covers. The first of which is knowledge representation and planning. This subfield first tries to structure data so that we can maintain facts in a computational system, so that we can later develop algorithms that compute actions to achieve goals over those facts. One concrete example of that field is a map navigation application. Now, if we turn our attention to probabilistic reasoning, one can think of this as really a subfield that augments all of the others. And really, this subfield is concerned with performing decisions when you have uncertain information about the environment in which you are performing your operations. So continuing with that mapping application example, if you know perfectly your environment, then you can just reach out and grab a planning algorithm from the knowledge representation and planning subfield. But then you will need tools if you want to start incorporating traffic patterns and other data. You'll need to reach into more of these probabilistic reasoning tools. Now, continuing around the blocks in this clockwise fashion, we also have the subfield that deals with communication, action, and perception. This subfield is really all about building algorithms that enable intelligent rational agents to interact with the environment. So let's say we take our mapping program, we zoom in, and now we're talking about a single car, and we need it to interact with both the humans and the other cars around it, and the infrastructure, say, in a major city. These are all the algorithms that basically provide the glue from harvesting the information, say from imagery or GPS, and turning it into actionable information for use by, say, a planning algorithm. Finally, as we round the loop, we get to the topic of today's lecture, which is all about machine learning. This particular subfield has just blown up in the past 10 years. Thanks to this confluence of mature algorithms and software libraries, as well as much larger compute power that we have in small devices all the way up to giant servers that sit inside of major corporations. But the key thing about machine learning is that what it's doing is using statistics to find patterns in data. That notion of patterns is critical in that the statistics is all about computing what's going on inside of your data, getting a better handle on whether there are trends. And so we're going to see here in this lecture today what makes machine learning really tick. To gain a better understanding of how machine learning differs from other approaches that we take to build decision-making systems, let's first think about, well, what does it mean to build a deductive system? And what I mean by deductive is we have to start with first principles. So that would be, say, in the case of robotics, which is the field that I work in, we would start with our dynamical equations of the robot over here and analyze our domain and problem. As part of that, we'll build a model of our system. We'll also do some form of stability analysis. And so at this point, what comes out of that process is a model with a bunch of other information that we understand about the system, which we can then zoom in on and develop some explicit algorithm to make it do what we want it to do. And pretty much all robots are driven by code. There will be internal electromechanical systems, but at the end of the day, there is a computer strapped to the top of one of these robots, and we will take that algorithm and turn it into code. And then that code is then sent out to the system and deployed. And as part of our deployment process, we need to create some metrics so we know if our algorithm really is doing what we want it to do based on the model that we synthesized. And then while the system is running, we will check out our errors, which typically come out of this evaluation phase, where we use those metrics to take measurements on what the system is doing compared to what we want it to do. We take those errors, and then we'll return back to the phases such as building our algorithm or reanalyzing the problem, maybe tweaking our model. We might have missed a nonlinear term in our dynamical equation. But all of this is a deductive approach. And machine learning, I'll show you, lives in the inductive world. So philosophically, when you go with an inductive approach, you are starting here with your data. You have a giant collection of data. You have a problem that you're trying to solve, but you do not have first principles. You do not have a model to start. What you are trying to do is build a model from the data. So our process to build this model changes from what we did in a deductive approach, because in deduction, we did all that analysis and out popped a model. Let's just say, trivially, it's a function of x, where x is whatever state space we care about, and y is whatever output that we are interested in. So this model in the deductive approach is just a function. So continuing along this line of thought, we will still start here. We'll analyze the domain and the problem, but here we don't have first principles. Instead, we need some domain knowledge and statistics to study the data and understand what makes up its statistical components, such as the standard deviation or the mean or other pieces of information that we use there. This information is used, we call it features. It tells us what we need to do when we select and train our statistical model. And from that process, this training process, which I'll describe in more detail, we do get a model. A model pops out on the other side that we can still deploy into some sort of computing system, but our model now is different. Instead of it just being the y is equal to h of x, we now have this new term, theta. And those are the parameters. So when we train a model, when we're building and when we're following an inductive approach, we are computing those thetas. We don't know the true function, the true model, say this h of x. Instead, we are approximating it. But then the remainder of it is the same. We'll still have metrics and they're absolutely critical. In fact, the metrics are what drive our training process. And we take our errors and we still analyze those, and we return to our design phase, and we have to restudy what the data statistics are, and then we may need to select and train a wholly different model. And so that is the difference between what we might do if we're building something from first principles to then taking a data-driven approach. So let's dive a little deeper into what makes up machine learning. So clearly statistics are involved. We've already had that discussion. But what are the pillars of machine learning? And I'd say we could break it out into three major categories. First off, statistics. That's already been mentioned. And optimization. So think calculus here. Anything you might have learned in Calculus 1, where you're taking derivatives and second derivatives, those are the foundations of optimization. And then finally, we have algorithms, the study in computer science of solving problems in a way that is repeatable and provably correct. Machine learning builds on top of all three of these. So in statistics, we need to care about, since there's data, we need to care about quantities like the mean, the standard deviation, and the variance. We also use a lot of probability distributions in machine learning. Furthermore, in optimization, though these are topics that are later in a student's studies, typically higher levels in undergraduate or in graduate courses, you learn about things like convex optimization and nonlinear programming. But really, at the end of the day, that's all about maximization and minimization. Oh, wait a minute. We already know what that is. That's computational rationality, which is part of our framework for AI. So now you see the connection that yes, we have statistics, yes, we have algorithms in machine learning, but that notion of building something that is computationally rational is leveraging optimization. And so then in the algorithm side of the house, we care about some particular algorithms, such as gradient descent, which I would argue is ruling the world right now because it's the main optimizing family that's used for deep neural networks. We also have to deal with a lot of matrices, and so we need efficient algorithms. So all of this together makes the machine learning soup. It should come as no surprise that machine learning itself has subfields. And the first of which we are going to build our intuition with is supervised learning, which is all about computing a model. So again, thinking about our notation, whenever you hear someone say a model, in machine learning, it is some function of X, which is our input data. So we think of this as one giant matrix of data, X. Think a spreadsheet. And then our target labels and values we call Y. Supervised learning seeks to compute the value of those parameters, theta, that best fit this model to the data. And there are two tasks that we use supervised learning for. The first of which is regression. And no, regression doesn't mean get worse. It means regress to the mean. That is a terminology from some of the early days of statistics. And so what we might do as an example is, let's say we have some housing data, a whole bunch of houses with zip codes and square footage and acres, as well as some prices. And we build a model. So in this tiny little diagram here, you see this blue line, and the blue line is a regression model. It is regressing to the mean of the data. And so we use regression to predict real values. And so you can imagine this as something when you pull up many different websites that might have a predictive price or some other predictive value, it's using regression somewhere in the background. But regression is not the only task that we care about. There's also classification. I'd say a lot of the buzz around machine learning is really brought on by some of these image classification problems that were very difficult. So yes, we as humans can see that is a very cute little kitten there. It just is waiting for someone to bring it a snack. But in computer vision, that was still a hard problem. And it turned out that if we built some neural network models, which again, it's a model, there's no magic here, we could have it produce discrete values. So it's no longer, say, $650,000. It is instead a discrete value of cat. And what we typically do is we'd represent cat as a number. It could be an integer, 0 or 1 or 2. But the point here is that it is discrete valued. It's not something that comes from the real number line. So now that we have supervised learning's definition in our hand and the key tasks that it does, let's examine more closely the process of building that model from our data. So what we have is this structure here. We've got our big set of data, X. We've got associated with every single X value, a Y value. To illustrate that a little better, let's look in the top left corner here, where I have a single sample, X0 from the data set. It's like a row in a spreadsheet. And then affiliated with it is some target value, this Y0. And so we take those pairs of the current sample, X0, and its target value, Y0, and we feed it into a magical process. So we're going to take all this data, and we're going to design what's called a loss function. So remember, computational rationality. And we're going to take this loss function and put it into the magic box. And oh, by the way, it's not magic. It's just optimization. So we feed in these pairs of data, the X and the Y, and we optimize to minimize that loss, basically between what the predictions are saying, or what the targets, the true values of Y, how they are associated with the X's in our data set. And when all is said and done, we get a collection of parameters that best fit that model. And once we have them, we then take those parameters, theta, and we put them into a deployable piece of software that implements the function y is equal to h of x theta. And then when new data that we've never seen before comes into our system, we then make brand new predictions and we're off to the races. So that is supervised learning in a nutshell. The phase on the left-hand side is called the training phase. And one could think of this on the right side is our testing and deployment. All supervised learning techniques follow this pattern. And oh, by the way, this actually smells like curve fitting. Curve fitting is probably something you've already done. And in fact, it is very much related to how supervised learning works. So on this left-hand side here, I have a simple plot, courtesy of this wonderful book called Pattern Recognition and Machine Learning by Christopher Bishop. And I have a ground truth sine wave, that green. But then what we do is we fuzz it. We get some noisy, we add some noise to that sine wave, and then we get our data. So all of the blue are little data samples, and they're represented in this simple little spreadsheet. We want to figure out what that data really represents. So let's just propose it looks like a polynomial. So there's that x is our data, and then you see all of the little parameters here. So the very simple example would be, let's fit a k equals 2, where k is what we call a hyperparameter, and that hyperparameter tells us how big the polynomial is. So if we say k equals 2, that will be a quadratic, and we stop with this particular term x squared. So that's great, we've picked a model, but how on earth are we going to fit it? So that's where we bring up our goal. And the goal will be some kind of loss function. And it might make sense that we care about the distance between what our guess might be, our model, and what the true value is. So we'll take that error and we can manipulate it in various ways. And one common one is to do what's called the squared error. And we would sum that up over all of the data points. And so this becomes our loss function, or at least this is an abstraction of our loss function. So once we've put it all together with every single data point, so we have I representing one of, we're going to run from 1 to n pieces of data and compute this error. We'll take this error and we want to minimize this error. So this process would be put into software, and after we run it, we'll get some results. Let's examine a few options where we have taken k and changed it. So that's again our hyperparameter. We're going to look at different versions of the model. So the first one is actually not that great. So if we just say make a single k value, that means our model is this very simple line. That's all it is a line. And there's a lot of error. You can see that when you look at some of the data points, it's pretty terrible. But if we somehow were right at these points, those wouldn't be too bad. But overall, we call this an underfit model. And if we crank up our polynomial, and I'm not even going to write that one down, so a ninth order polynomial, it looks amazing. Holy cow, we got that one, we got that one, we got that one. Whoa, wait a minute. Wait a minute, there's all this other error going on here. All the other spots there. And so what happened was the optimization process really wanted to fit that polynomial. And so you're going to have these crazy values of theta that make your system overfit on the data. It means it will be brittle. And if it gets any other data point that is not those particular ones we provided it, it will not work well. So there's got to be a better way. So, I experiment. And I say, how about k equals 3? And like Goldilocks, I found the exact porridge that was not too hot and not too cold. And this is a model that certainly qualitatively we can look at and go, yeah, that's pretty good. It kind of looks like that sine wave. But also notice that it really hugs the middle boundary between all of those different pieces of data out here, trying to soften the blow of the error for all of those data points. And so this is the crux of a lot of these machine learning techniques. We have to continually tune these hyperparameters to find the model that fits the best. And the field of supervised learning has a lot of techniques, and I can't cover them all in this short lecture. But a few big ones are taking this model h of x theta, and we could say use a decision tree or a support vector machine, or the neural nets that are all the rage right now. And I encourage you to go check out what all of these different types of algorithms do. And probably you will learn more about them in future courses. But this is the framework again, that we are building models. And each one of these types of techniques, at the end of the day, builds a function y is equal to h of x theta. So we have supervised learning and, oh, wait a minute, what's this unsupervised learning? It sounds kind of bad. If we just let something learn unsupervised, that'd be like letting my kids run around with markers and draw on all of the walls in the house and no one ever tells them no. It's kind of like that in unsupervised learning in that we're still trying to build a model, again, something that looks like y is equal to h of x theta, but we have no target values. So we don't even know what we're looking for. It's just the y is missing. We just have this giant collection of data x. But that doesn't mean we can't do anything. It turns out that unsupervised learning has a lot of valuable techniques that end up being used in a pipeline where you can combine them with with supervised learning techniques to achieve some powerful outcomes. The first thing that you can get out of unsupervised learning are these algorithms that deal with clustering. So it's more of a statistical analysis. We have our data and we do some educated guessing on, you know what, we know there might be 3 or 4 categories. So we use a clustering algorithm to try and seek out if there are some collections of data that amass around certain clusters. And so this particular algorithm here is trying to move, so the darker shape that's in the middle of each one of these clusters indicates some center of mass. And so we use those clustering algorithms to help us figure out if there's an anomaly. So if some piece of data all of a sudden pops in that might be way out here, it's not really in any of those clusters. And then if we start seeing, uh-oh, more data coming in, more coming over there, well, we probably need to rebuild our clustering system with 5 clusters. So really think of it as a way to get a little more statistical insight into your data. Another very powerful collection of tools are the ones that do data transformation. So if we have this really complex data, such as what's called this Swiss roll. So think of it as one of those little Debbie Swiss roll cakes that you might eat when you're having poor judgment in what kind of things to eat. We can actually take some really robust mathematics and smash it from 3 dimensions into 2 dimensions, which is the image on the right. And then that actually will help our other learning algorithms work better, both in training and in execution. They'll be more efficient. Reinforcement learning is the final subfield of machine learning. And this is all about computing optimal behaviors for our systems via trial and error in an environment. So what I mean by behavior, the common term in reinforcement learning is a controlled policy. It's when I'm sitting in a particular state, I'm an intelligent agent. What should I do next? So if you like video games, maybe you would say, build a software agent. And that's my Mega Man representation. And Mega Man's going to take actions in the environment. And as Mega Man takes actions, Mega Man gets a new state, sort of where is Mega Man right now? Is he jumping in the air? Is he shooting a energy pellet at Metal Man? And also Mega Man will get a reward, at least the agent gets that reward. And as it explores the space, it starts learning some control policy, which we denote by pi. And it's a policy that takes the current state of the world and moves it to an action and takes the agent to somewhere else. So reinforcement learning is this field of study where you are developing algorithms to compute those policies. And more recently, people have had some success with mapping it to real systems, but you need a ton of simulation. And in fact, simulations, because they are derived from first principles and they are approximations themselves of what's happening in the real world, it doesn't always transfer to the real world. So you need to do, as in this case, you see there are 4 different robot arms doing something. So in the real world, unfortunately, we have not yet figured out how to scale this. So there is a lot of trial and error in the real world that just will not scale as well in this space. But that is a topic of research. Now, machine learning is what I've presented so far. I've given you some of the techniques and the principles behind it, particularly in supervised learning. But there are practical aspects that you have to pay attention to. First of which, we need a lot of data. So anything like an image classifier or natural language processing, you end up needing gigabytes to terabytes of data to train realistic models. But also lots of data isn't always good data. You have to make sure that it's really relevant. Is this the problem you're trying to solve? So if you're trying to build the world's best cat classifier, but you don't feed a lot of cats into that, or images of cats into that classifier data, instead it's lots of dogs and people and cars for some reason, that will not build a good model. And you also must have clean data. So lots of data sets that are real, we're missing some of the features that we really need to make it workable for a machine learning model to really build up some statistical association of the data and the labels that you're interested in. In addition to those practical considerations, just consider for a moment all the work that has to be done to make these things go. So there was a paper by Google that talked about all of the hidden, what they call technical debt. There's all of this stuff like configuration and data collection, data verification, all this stuff around a little teeny tiny algorithm. And believe it or not, all the stuff I told you today, especially with supervised learning or unsupervised learning, these are library calls. So this particular library is called sklearn in Python. In 3 lines, I have a model. But to get to that model, I need all of this surrounding stuff that is really a giant systems engineering challenge. And when you are building something at scale in a business, this can be very expensive. And so you have to be aware of that when you are building real machine learning systems beyond what's built in academia. Let's close out this lecture by taking a step back and looking at the big picture with machine learning. First off, we should now know from this discussion that machine learning is not magic, it is optimization, and a very good use of statistics and algorithms and optimization all rolled into a giant technical furball that provides value. But that value really only works in narrow problems. Machine learning is not going to give us generalized AI or some of these things we see in these sci-fi movies where you might have something like Hal from 2001: A Space Odyssey making these crazy decisions that are like a human. Instead, machine learning is a piece of the puzzle. It's going to help you build that individual home price regressor or that cat classifier, which then would fit inside of your larger AI solution. And finally, machine learning, because we're doing this inductive approach. In deductive, if you were building an algorithm from scratch, you might have heard the term garbage in, garbage out. In machine learning, because it's inductive, it's more garbage data in, garbage data out. So we are now trading our engineering effort from doing, say, a deductive analysis approach to now doing a lot more work on our data. So you have to make sure that you have lots of clean, relevant data, and then your machine learning solution will work. So that's it for machine learning. And I hope this gives you a few pointers and an index into the field so that you can continue to study in the rest of your career.